So after a little bit longer coffee break, I would like to welcome you to our last session today. And we will start by a talk given by Olga. So thank you.
Hello. Oh, wow. My name is Olga and I'm from ROIVANT. Looks like it's only me and Henven who stay between you and going to the beach. So I try to be quite condensed, but nonetheless, I hope it will be interesting. A lot of the stuff I will be talking about has been already discussed by previous researchers, and I think it's great. It means that the topic is very important for other people. I am from ROIVANT, and I work in the part of team which belongs to the QUAISAR platform. And many of you may be familiar with you may know Silicon Therapeutics, and great person from there, Woody Sherman. So Silicon Therapeutics was acquired by ROIVANT last year, and now this all has been transformed in the QUAISAR platform, which is specifically designed for improving the methods in computational drug discovery, introducing the new methods and making the drug discovery to be more easy, more faster, more efficient. And in our world, we had several talks today about the importance of not only today, but in the last few days, we had the talks about the drug discovery, and that is not really very easy, and that the chemical space of the possible drugs and the opportunities there seems to be absolutely infinite. And I think it's a big area for development and introduction of new methods. And in our group, we pretty big group, we do apply and do develop different approaches. We combine them together to make the better solution for prediction of the drug and to make the drug discovery to be efficient. I work specifically in the team that is focused on the development of force field, and not much of the we're not really much of focusing on inventing something new or rocket science, but we really focused on making the force field to be accurate, because as more accurate is your force field, as more accurate will be your simulations, as more accurate will be prediction of the binding energy or conformation or other events, as less you will have to spend on doing the redundant experience or experience that bring you the false results that are more accurate force field will lead you to the more careful prediction, and a lot of time will be used for things which are more important rather than running the redundant work. Right, so we name it force field engine, or shortly FF engine, and it uses different tools and it uses different approaches and methodologies in order to improve the computations. It's largely based currently, it was something that was inherited from Silicon Therapeutics, and it's largely based on the Amber-Gaff force field, but we still aim to improve it with the new methods, specifically the part that related to modeling electrostatics and the part that related to modeling the torsions and conformations of the small molecules. And yeah, I know that some of you can take can be very sensitive to that picture on the left, but please take it with a grain of salt, because it's a little bit out of dated results. And after that, we have I know that both of the force fields were redeveloped, Smirnov and Gaff, and also the ROIVANT also was brought to the new upgrade, and numbers probably would differ, but keep in mind that we are very much driven by application. So all the work that we do for the force field development, we aim to be specifically to make the force field to be as accurate as possible for the application that we run. Right. No need for me to tell you what is the force field, but I just want to reiterate it to make sure we're all on the same page. The classical molecular force field has the different interactions, and each of these interactions has kind of standardized representation, functional representation. Each of this functional representation has a lot of parameters that needs to be fit, and the question is that how you fit these parameters. And the general approach that has been utilized by people who run the classical MD simulations is using so-called atom typing. When you describe the chemical environment of an atom with the rules, and you assign you basically approximate every chemical environment with a specific atom type. In some sense, you can think about it as the coarse graining of chemical environment. Then when you know that your molecule can be split in this coarse grained chemical environment described by the atom types, you can have a lookup table where each of this environment will be described. So for example, the bonds between C1 and N1 can have specific parameters in the table. The bond between O1 or C3 can have specific parameter in the table. And in this lookup table you use in order to run your simulations. We start to think about it, and I guess something that has been extensively discussed by John Kader is that the amount of atom types can be enormous, and amount of chemical environment can be enormous. Even here, if you look at the carbon, we're a small molecule of adrenaline, and it's already around 7 different ways to place the carbon within the vicinity of other carbons. And nonetheless, you can keep running creating new atom types, but every new atom types will introduce the challenges in parameterization and reparameterization, because you need to take into account to also modify the other parameters which were already introduced for the previously known atom types. And then at the end, we know pretty well, there has been done a lot of work for parameterizing the large classes of molecules like proteins, lipids, nucleic acids. Small molecules is still something that people are trying to find the good parameters for, and we had already heard a lot of talks about it that people discuss significantly, but discuss this significance. But nonetheless, you will be always your accuracy of your computation will be always bounded by the atom types. You're only as accurate as your atom typing and the scheme of parameterizing the force field based on the atom typing. And on another side, when you think about it, it's that atom typing is a very weird way to describe the continuous atomic environment. And if you think about it, that what you do is actually you come from the continuous representation of the atomic environment into the squeezed latent discrete representation, and then you go back to the parameters which are also continuous. So the question is, do we really need this approximation? Do we need this loss of information due to discretization, which is highly rule-based, highly human biased, very well established in the field, but with the new approaches in machine learning, I think we can do it better than it is done with the atom typing. And actually, yeah, so the reason why I put this picture here is there is a very cool discussion about it in the book, is that actually the painting masterpieces, they consider to be the one which contains the most of the information. And you can actually see it. So whenever you have something that has less information, it's not that appealing as something that has more information per square centimeter, I would say. Anyway, I myself very much a big adept of the idea of using the continuous representation and so-called atomic embeddings. And in this work, in this topic I want to talk today, I want to tell you a little bit what I have done, what are the steps that I have done during my time in ROIVANT toward moving away from the discrete representation towards to the continuous representation of atomic environment, and where we see it to be used in the future and how it can be applied in the future. The concept here is pretty easy. So you have a molecule, and emergence of the graph neural networks allow you to represent the molecule as the graph, and then with every node and every edge having their own features, and then you pass it through the graph neural layers, graph neural network. And in the particular work here, I used the transformers, which is described very well in this paper with some modification. in general, you can use any model here, I'm pretty sure, but I use few and I like transformers very much. And I actually did some modification, also search for the parameters here substantially. So if someone is interested in the technical details, we can work more on it. So the thing is, the idea is the following: you have the graph neural network, you have the transformers layers, and then what you get at the end is the vector per atom, which we named atomic embedding. So to be specific about the terminology that I use here, whatever goes to the nodes is the discrete features. Whatever going out from the GNN is the atomic embedding, it is continuous. Then this, you want to think about how you would train this network, and people can use various approaches for this. We took that as an initial idea in the task classification of the atoms according to the atom types. And for that, we use our internal atom types. It's about 500 atom types, which are largely extended in order to take into account different features of the torsion angles. And it's based on it's far away from Amber, and it's based on the a hierarchical representation. Maybe I should have put here the link to the paper, but if you're interested, again, I can send you the paper. Anyway, so around 500 atom types. Each of them have the hierarchical way of assignment based on the environment of the atom. So we take the model, which consists of the 3 transformers layers and then classification layer, to predict the atom types. The model is getting trained, it predicts the atom types. And then what we eventually want to do, we want to throw out the classification layer and only use whatever is produced by the graph neural network, what we named atomic embeddings for the future work. So one of the questions that comes here is that how would you train this model? We have a substantial amount of data sets available. But then when I started to work with this, I soon realized that if you look at the amount of if you assign the atom types to all the data in Campbell or any NMI or anywhere else, all the molecules are very much similar. So that's why you will have very skewed distribution over the atom types. Some atom types are overrepresented, some atom types are very underrepresented. So is there the way that we can construct the data set that will be more or less uniform? Because every time when you take a molecule, you will always have some atom types which will be only once represented in the molecule, and the rest will be overrepresented, like carbon within a ring. So I was thinking more about it from the point of view of information theory, and I think I tried to talk to Luis about it also. And now I'm thinking about introducing also your method. So the thing is that what you want to achieve, you want to have the subset of data, which will have the maximum information. Your information is it's a quantity, it's not the abstract word, it's the inverse log of the probability of the event to occur. In some sense, as more often the event occurs, as less information it brings. As more rare the event occurs, So as more often events occurs, less information. Rare events give you most of the information. Like this is rare event, this workshop, which happens once in a year, and it already provided us with a lot of information. The expected value of the whole information of overall the events is the information entropy. And usually when people do the machine learning, when they do maximization, they do optimization with respect to cross entropy. That is exactly in order to reduce the amount of information loss when we model the distribution with the neural network. Nonetheless, when I thought about it, I first decided to check what if I consider it as the function, so how it actually correlates with the data that I have. And you can really see that entropy is really very well correlates with the number of atom types in the molecule, which makes sense. And it does not really correlate with the size of the molecule. So you have a lot of small molecules with the diverse atom types, and you can have a lot of large molecules with the same atom types. It's information content of the small molecule will be larger than the information content of this large molecule. And by definition, the uniform data set will have the maximum entropy. With the almost 500 atom types, it's around 6. I did a bit, so I generated the data set. I have decided to go greedy here. So there is so-called greedy algorithm. And what I have done was that first I wanted to see how the data usually behave. Actually, I should have swapped the slide. Yeah, let me do it first, this slide. I used the CREM framework in order to generate artificial molecules, and specifically the one which have it's fragment-based tool which generates the molecules. So I choose the fragments that have the most rare atom types as generated molecules based on them. And then I found the subset of molecule which contains, which brings me most of information, because as it was stated before that it's not the amount of data that we need, it's the content of the informational contents that we care about. And right, so going back here is that you can see is that how I would choose this subset. It's I took all my I choose the greedy algorithm for that, because the problem is it's an P problem to find the subset which maximizes some property. And I just took all the molecules in my set which I generated. I computed the information, carried each of the molecules, sorted them according to the information content from the maximum to the minimum. And then I started to accumulate the data set, adding one molecule per time, and then I compute the total information content of the data set. This is inequality. It's not the when I do it, it's not that the information of the data set is the sum of information from the content from each of the items, but it is the upper bound. So it's a pretty good way to at least have an estimation. Surprisingly, what you can see up at some point, you have an increase of information content in your data set. And then regardless of how many data points you add, your information content either doesn't change or it decreases. That was very interesting to observe. And actually, that's how I picked up my data. At the end, I ended up having 7 million molecules because aside from this choice, I also did some manual addition of the molecules with the rare atoms like metalloids, for example, silicon and so on. Right. Training set, trained the model and then tested it on the data set that we already have. And as you can see, so the accuracy was calculated actually not per atom, not which atom is predicted correctly or not, but accuracy was calculated per molecule. So if all the atom types were predicted correctly in the molecule, then it's correctly assigned. If at least one is wrong, then it's incorrect. So as you can see, we are doing pretty good job on prediction of the atom types with the on most of the data set, a little bit worse on the charged molecules. I need to figure out what's going on there. Because, yeah, I don't know at this moment yet. Please don't ask me. Right, and the thing is that what I try to say is that one of the important things that we found here is that the mistakes of the neural network, of the graph neural network, are pretty often we encounter that mistakes is because the assignment of atom types with the rule-based approach is very ambiguous. And it's not that this is the wrong. There's several ways to assign the atom types, especially when it comes to, for example, NMN dataset or DRD2. Very often the network gets confused with the atom types, which is in the fused rings. And this is what we found that also become one of the justification for us that the atom types assignment is very much human biased, and a lot of times we do not take into account all the information that is about the molecule in order to assign the atom type. So that was also one of the hints for us that the atom type assignment that we use right now and the formal and the rule-based approach might not be the best case scenario. Nonetheless, atom types was not actually the purpose. The purpose was to train embeddings. And the first thing which I wanted to try is to see what actually my embedding shows, if they are any meaningful or not. And I was doing PCA analysis, and I plot the PCA components of the embeddings and how they look in the 3D space. There are just few images, but the top one shows you, for example, if I color my embeddings according to if I only plot the embeddings for nitrogen atom, and I color them according to the amount of neighbors that the nitrogen has, so you can clearly see a few clusters. The red one, very red one, it's can you guess what it is? It's a nitrogen with a triple bond. only one neighbor. So the blue one and orange, they're very much fused. They are, I believe, two and one neighbors. But the most interesting is actually the ions. So the clouds that you see here is the different ions. The bottom one, I guess the purplish, it's the, I think it's fluorine. The turquoise is the chlorine, and the greenish bulb in front, it's the sulfur. Again, why we have two bulbs? Any suggestions? So the top bulb and bottom bulb is that the sulfur with the valence 2 and valence 4. So that's what I can see. There have been more analysis done, just the most representative, showing that embeddings trained in this very simple way can indeed pick up the environmental information about the atoms. Nonetheless, we were trying to make it more applicable and see how it can work further. And we work on the predicting the parameters of the force field, giving the atom types. So what been inspired by Paloma, we used the Janussi pooling model, and but we trained it. So the only difference was that we took to predict the equilibrium bond end and bond angle, for the reason that we could train it against the experimental data. So we had the crystal structure database, and we took it as the assumption that the experimental result, the crystal structures of the small molecules, is the ground truth. And we predicted against them. Yeah, the only thing that you give is the embeddings that has been already pre-trained. You do not retrain embeddings, you only train one pooling, you only train the pooling model to predict the value, one value of the reference bond or reference angle. The test that has been done was done against of the molecules that have been optimized with the QM ORCA, and these molecules were not in a training set. So what you can see is that the model actually, the blue is the reference bond, the red is the reference angle. Knowing nothing about except for embeddings, about the data, and being trained only on experimental data, it can behave as good as QM. And the only thing that you can see here is a little bit bulb is the hydrogen, because crystal structure database does not really treat hydrogen very nicely. And it needs to be retrained only on the neuron diffraction data to make sure that hydrogens are also experimentally resolved. Bottom line is that embeddings can be used, these embeddings can be used for predicting the parameters of the force field. And I'm currently working and I have some preliminary results on predicting the torsions and predicting other parameters as the bond and angle strength constant. And but I'm not showing it here. It's still work in progress. There's still some little things to do, but the results are very promising. But another important stuff that was, so this part of work has been done by my colleague. And what we try to do, we try also implement the embeddings in our model that estimates the charge. And we've been already talking about the predicting of the charges of the molecule. We know very well that RESP calculations are very accurate, but very slow. And the approach that we utilize is also, many of you familiar here, is the BCI model. So there you have the pre-charge and you only compute the charge, which is partial charge, which is due to transfer of the electrons. And so what happens here is that this work has been done by my colleague, and what he noticed is that most of the time you lose the information about the partial charge because the atom types are not presented in a partial charge table. So you have to think about the scheme, work around, find the similar atom types in order to find this correction term. But with embeddings, you always have. So what he has done was that he took my embeddings and then he put it in the model and then trained this layer of predicting the charge. And then he can produce the charge. So basically, giving only embeddings, you can always produce the partial charge. This is the great example of being from continuous space, you're still in a continuous space. You don't need to go to the discrete representation of your atomic environment and and use the lookup table. And of course, it actually behaves as accurate as RESP, but it's way more faster than the rest. I think I will stop my somewhere here. And what is next is that one way to use, one way we are looking forward very much to creating the fully ML-based parameterization of force field. And I think I should say hi here to Daniel Cole and Sean Cadera. It's really cool to see that we're on the same page here. And I really hope we can join our forces in this work and make force field great again. And right. And another important thing, which I'm also a big adept of recycling of the models. It's not always convenient to use the model, to train the model every time when you have the new task. And one of the way we want to use the embedding is building these molecular fingerprints, which will be based on the aggregation function. You train aggregation function to gather information from the embeddings and create the one vector per molecule to predict the molecule properties. And on another side, you can branch out and use the per atom vectors at the same time. And we really would like to have it to be more or less uniform, so people do not have to retrain it every time when they need to, when they find a new data set, or they try to predict different properties and so on. Right, so this is our team, and these are the people who work on the force field. Not all of them do machine learning. Some of them are normal people. This is how we contribute with our brain work into global warming. So a lot of these people, they work on the different parts of the force field and the different methodologies implementation. And I really hope that, and I'm really glad to be here. And I thank you very much for inviting me, because I can see that there is a lot of opportunities to create, to build our work together, because we try to solve the same task, basically. We try to find a way to address the scientific questions. And joining the forces would be the great, and this bonding, although the bonds do not exist, it's also a very good opportunity to share the knowledge and make our work to be more enhanced and more useful in the future. Thank you so much.
Thank you for the very nice presentation. I already see a few questions in the audience.
Hi, very exciting talk. I had two linked questions. The first is for these force fields that you're making, is your plan to have these hydrogens be flexible or for them to be fixed?
Flexible?
The hydrogens.
I don't know.
Okay, fair enough.
I actually like the note from Johnny yesterday. Hydrogen are useless.
They're kind of useless. They're kind of horrible.
So the thing is that I do not really run simulations. I cannot say for sure. I only get the information from people. If this is work, it doesn't work. I guess we will try different approaches. So the way how it works is that we try everything, whatever works first, then we go with this.
I guess my follow-up to that is because you were mentioning that like the CSD hydrogens are they're not great in terms of like their positions and figuring out like the equilibrium angles and distances for parameterizing your force field. It makes that difficult. Is that a problem you can solve with some amount of either QM or some of these ML models that have already come out and get all the short range stuff right? Can you relax the hydrogens with that and like get a sense of where they should be to correct off of the CSD?
So yes, this specific question needs more exploration, I would say, because in my opinion, that from what the tests that I have done is that a lot of force field that we have, they're pretty good, but they're also pretty bad. And I don't really like comparing force field with each other. And I think that we need to have more work here. I don't really think that I don't know if there is the way to solve this problem only with machine learning, or it indeed needs QM, or maybe the whole approach is wrong. Maybe we need to think about something else. Maybe there should be a way to get rid of hydrogens indeed, and then incorporate information about hydrogens in machine learning potential or machine learning parameters. Well, there is a lot of ways to explore it, a lot of directions.
Hi there. Yeah, thanks for a great talk, and I agree. It's good to hear we're on similar pages. I appreciate you might not be able to say, but for the bond and angle force constants and torsion parameters, are you building your own quantum mechanical data sets, or do you think there's enough information already out there?
So currently, the proof of concept training model was done for Ambert parameters, but yes, we are building our own data set with the parameter of. There's a bunch of methods that are used to find the good parameters that can always test it on the real data. So I'm not building that data set. I cannot give you much of detail, but yes, we are building our own data set for training these models. We basically do right now perform very routine and very slow running work in order to train the ML models and do not do this slow routine work anymore.
Are there any more questions?
Yeah.
Yeah. Perhaps the next speaker can set up with the email.
Maybe a quick question. How you see this collaboration? Because the typically industrial companies make all their force field proprietary.
Force field, yes, but not the methods to implement in the force fields. The methodological part is most of the time is shared. And what we do right now, we do not reinvent the bicycle. We are using most of the work that has been already done. And I don't think that my part, the method part, is not really. It's not really under the any disclosure agreement. It is purely research, and it's not really. It doesn't have any intellectual property that can be closed without sharing. So that's why it's public. I think that methodological part is very much shareable, and the data, yes, the data is more difficult. But if you have the product, I'm pretty sure that if we have the product which has been trained and it shows that it all performs everything around, then of course it will be shared with the paper and we get all the credits. But I don't think we're going to be there soon. And when I mean collaboration, I mean mostly regarding the methods rather than the final product.
Let's thank our speaker again. And